the photon energy density we observed today. So this, if we want to explain this observation, we need to have the out of equilibrium dynamics involved in the early universe. And then we also have the strong dynamics, neutrino mass problem puzzles, and the strong CP problem. And also we want to ask the future, what the theory should move on. Should we have the ground unified theory or like even string theory? And so for the experimental test, we want to ask what we can learn from the precision measurement. And this requires some our reconsideration of theoretical inputs to colliders. I would point out this specific one, which is about the parton distribution function. You can think about this as when you collide two high energy protons, and what coming out of this proton is the quarks and the gluons. And these are the particles that is really in the collision. And then we can produce Higgs, WZ, and W bosons and Z bosons, all of these particles you might heard about. And then we want to, our theoretical input in this process is this one, the parton distribution function. Basically, it is the probability that you can kick out one proton or one quark or gluon with a specific momentum. And we don't know how to calculate this property, these quantities yet, to a precision level. As you can see here, for the future high LUMI LHC, which is operated at CERN, the theoretical prediction, the theoretical uncertainty in the future, theoretical uncertainty is denoted as the gray bar here, which would be much larger than the statistical uncertainties that we could provide in the high LUMI LHC. So they should question our input about this, the theoretical predictions for specifically this process. And you zoom into the uncertainties, you will notice the most insignificant contribution to this uncertainty is this parton distribution function. And then we would like to explore new calculation tools for this specific observable, and then improve our capability of high-end future colliders to explore new physics. And you might already know this as PDF involves real-time strong dynamics. As for strong dynamics, we know there are classical Euclidean calculation, the non-perturbative calculation, which is the Euclidean lattice calculation. It's based on this Monte Carlo method. I can give you a brief introduction to the method here. So it's basically a sampling procedure. Suppose if I do not let you open this box, open this bag, that you can take one ball out of the bag at each time. Then I want to ask a question: what is the probability? What is the portion of the red ball over this among all of these balls, right? So then we can take take one ball at each time and then calculate the probability for as we're accumulating this procedure. So this is a sampling procedure. Then you'll get the correct percentage as you repeat this procedure for like a sufficient time. However, I would like to point out that the weight you want to put for the blue ball and red ball is proportional to a specific quantity. This is the exponential of minus action. However, if for the quantum field theory or calculating the real-time dynamics, this SC, the action, is not a real number, could be like an imaginary number. In essence, this weight is not well defined, right? It's not positive. When you calculate the probability, you will have negative numbers here and in the denominator. Then when you sum up all of these weights, you are getting some like accidental cancellations. That means you need to do this procedure for a really, really long time, exponentially large number of the repeating time. So that's why this is the famous sign problem that is caused the questioning of the Euclidean calculation of calculating the real-time dynamics. And then that's why we come to the quantum computing for those kind of processes. Basically, for the quantum computing, instead of doing the weights, doing the sampling, you can do a real-time dynamic. You can do a real-time simulation. Basically, you can prepare some state, and then you evolve the state under the unitary time operator, and then do the measurement. So this is equivalent to the the passing real-time path integral, which is different from the Euclidean one, which is the imaginary time in the path integral. And this is quite a new field, and there's a roadmap written in 2023 trying to quantify all of the questions that we have in this field, and what are the simulation method that you can use quantum field theory or effective field theory. And we also like a question picture what simulators we would need, quantum devices we would need, and software and compiler that we need to develop. So this is a really new field. And then let me introduce you a little bit about the current status of quantum computing on the market currently. So basically, we have different basic units for the real device. For example, you can build up the quantum computer based on the superconducting processor or multi-chip quantum processor, and photon qubit or trapped ion. So now for the most advanced one we have. Is there a question or? Okay, so right, for the superconducting processor, the IBM that recently updated, they have around 1,000 qubits, and now with iCloud also, from the internet, we can get access to 133 qubits. And for the photon qubits, this is the 9章3号 in China. They can provide 255 qubits for the real device. And also recently there's this QERA company. They announced they can reach 48 logical qubits. This is with error corrections. So all of these numbers here, beyond the QERA one, they need to correct for the errors and then build up a smaller number set of logical qubits. So this is the current status, and actually, the progress of the hardware is really fast. That's why this is a very nice era for us to consider simulating quantum field theory on quantum computer. Also, if you look at the futures, you will notice this is an IBM roadmap. Basically, after 2024, the qubit number will not increase too much, but they will try to improve the number of gates. And for the innovative roadmap, they will also focus on the modular operation and also the error corrections for this real device. So I hope the previous session is sort of understandable, and then the later part will be a little bit technical. So I will try to make it clear and simple. So then it comes to the real question: if we want to simulate a QFT on a quantum computer, what do we need? What are the problems that we need to solve? Right. Basically, you want to build up the whole algorithm, which would include discretizing the space into lattices. Otherwise, you will have infinite degrees of freedom that cannot be put on the quantum computer. And then with this discretization, you want to ask what is the Hamiltonian related to the system that I want to simulate. And then there's this digitization procedure. So basically, even I discretize the space into lattice at each lattice point, my degrees of freedom is still infinite, because if I consider a scalar field theory, the scalar field can take any values. It's a continuous value, so that's infinite number of degrees of freedom. I want to truncate this infinite degrees of freedom into a finite one. This is called the digitization. And there are a lot of methods that people are still considering which one is the best for the QFT, the gauge series we have in the standard model. Otherwise, and then you need to initialize the state. For example, as the system is built out of quarks or gluons, you want to prepare the you want to prepare the proton state and then let these two proton states collide. So afterwards, you want to propagate the initial state prepared. So as our QFT provided the most dense Hamiltonian, we need some approximations to construct this unitary time evolution operator. There are totalization, variational approach, and Taylor series, or etc., which are still under scrutinization. Then we want to evaluate what are the observables that how should we measure the observables that we're interested in? For example, if I want to measure parton distribution function or particle decay, what should I do? How do I do the measurement? Right, involved in all of this step is also the error mitigation and the correction, because we have quantum noises. We want to also develop the most efficient error correction code for the QFT simulation. And then I will give you a bit of details related to each part. For example, the discretization part. If I consider the gauge theory, specifically we consider electromagnetic field, we know when we do the, we know we have a Hamiltonian, right? Because for quantum computing, we need to develop its Hamiltonian. Like in the continuous space, we have the Hamiltonian, which is the E square plus B square, right? Electric field energy plus the magnetic field energy. Then you have the Hamiltonian integrating over the space. However, if I do the discretization, the space becomes like discretized, right? It's a lattice. I want to preserve the gauge symmetry. So this would bring this E square into the lattice E square. So this one, this E electric field with respect to the continuous one has some errors. It's proportional to A square also. A is the lattice spacing that we do the discretization. And the magnetic field square is a B square, would be written as the Wilson loop. This is a plaquette. It's a square on the lattice. So basically, you consider the interaction between the four links that constitute this box. Right. Then we have the gauge invariant Hamiltonian. Also, we have fermions in the standard model. We are going to construct this fermion connected term and also the mass term here. So basically, this is the Hamiltonian for electromagnetic field plus fermions. And then the question in this procedure you want to ask is whether this is the only one, the only Hamiltonian. That's actually not. For example, if I want to consider improved Hamiltonian, so previously for the Kogisaki Hamiltonian, I'm only considering this red box. But if I want to improve the Hamiltonian, improve its convergence to the continuous space Hamiltonian, I can include higher order interactions. Basically, I can include this rectangular loop. And for the kinetic term, instead of considering only one link kinetic term, I consider this two-link operator, two-link interactions. So this is the improved Hamiltonian. And then you want to ask what are the benefits? Will include higher order corrections, right? Whether it really improves the convergence to the continuous space. That's those questions has to be demonstrated, and it's still like a under study. And then let me talk about the digitization part. There are a lot of interesting things to look at when you study the digitization. This is to truncate the continuous field variable into finite ones. And we have a lot of methods. This is a list of some of them, and with the authors followed. So basically, which method is the best is still under like a scrutinization. We need to consider the rate of convergence to infinite dimensional theory and the resource requirement. So we want to preserve the local gauge symmetry and ask. So we want to ask a question: which method provides the best way to preserve gauge symmetry? Right. So this method has recently developed. There are a lot of things to study, and I have been focusing on these two of them. One is the angular momentum basis. Basically, you truncate in the basis that is diagonal. That is the diagonal basis of the magnetic field square, the B square term, or the Wilson loop term. For this structure, is very similar to the momentum cutoff that we studied in quantum field theory. And when you increase the cutoff, you will expect like a faster convergence or the convergence to the continuous theory, right? This is demonstrated for a specific observables like the plaquette vacuum energy studied in this paper. And then as you can see, when the x-axis increase, which means you have a larger momentum cutoff, then the result will converge to a specific value. That will be the standard, the continuous theory value. And also there's another method I have been focusing on. This is a group element basis with you truncate with discrete subgroup. This is, for example, if you want to study U1 gauge theory, which is electromagnetic field, the U1 gauge theory. And then instead of studying U1, you can study Z100 or so, Z100, Z200, Z200, and then we'll take the Zn, n goes to infinite limit. You are going to approach the prediction of U1. That's the discrete subgroup concept. So for the standard model, we have non-abelian gauge symmetries like SU2, and it has its own discrete subgroup that could match very well for specific couplings to the SU2 gauge series. Also, there's a very interesting aspect related to the discrete subgroup. As you know, like you will consider U1. If U1 is spontaneously broken with a Higgs developing a wave, then you can the broken the group that after the broken could be a discrete group, right? This is a very nice mapping between the continuous group and the discrete group. Basically, the difference is they will have a Higgs mechanism. And the question is, this has been like studied in 1970 for U1. However, for non-abelian gauge symmetry, this is still like there are not so much study, and we don't know what Higgs representation we should put if we want to break the continuous group into a specific discrete ones. Also, with the discrete subgroup, so this plot on the right shows you what are the predictions based on the continuous group and the discrete subgroup as a function of 1/g squared, right? So if I really want to use discrete subgroup to match the continuous way, I want the blue dot and this green triangle to match, green rectangle to match each other, green square to match each other. However, at specifically a very large beta or small coupling, you observe this discrepancy. And then the question would be, how do I improve the convergence or the consistency between the discrete group and the continuous group? There could be the improved Hamiltonian also, as I previously discussed, or you can consider a larger discrete group. This would be a bottleneck for discrete group digitization, because for specific non-abelian gauge group, it only has a small, like finite set of discrete group. Basically, you cannot take the infinite limit and reach the SU2. But as you improve the Hamiltonian, you might already in some regions that the areas of A squared, the power law of the lattice spacing, or some other parameters, you can extrapolate to the continuum without considering a larger discrete subgroup. But those problems are still like under investigation. So those are questions that I'm interested in. And then there's this very nice Gauss law involved. We have learned the Gauss law in the I think in high school even, but probably definitely in the undergraduate school. So the Gauss law is the Gauss law basically saying if I consider a flux coming into a point and going out of the point, the difference should be equal to the charges sitting on this point, right? They have charge conservation. Then this is the Gauss law. For the digitization measure, that this also involves the Gauss law, because if I want to prepare my Hilbert space for a given Hamiltonian, I still have some redundancy from gauge transformation, right? That means I will include equivalent copies of each gauge sector, and this sector, like for each copy individually, they do not satisfy the Gauss law. If you count the charge, then there is no charge conservation. But if I apply this constraint, I will construct a gauge, like a charge conserved state. So basically, the state in the Hilbert space need to satisfy this condition. Under the operation of the Gauss law operator, it gives you zero. This is a charge zero state. Then the question is whether I should include the Gauss law in my when I construct my Hilbert space, right? I want to give you an analogy to the quantum error correction code, because this is a relatively simple example to demonstrate this gauge equivalent sectors, or gauge redundant sectors. So, for example, if I consider my Hilbert space as only to be these two, but when I do the encoding, I need 3 qubits. As I encode my information into precise state, for the quantum error correction, I will add 2 accelerated qubits. So the full qubit space is actually dimension 8. But when I use some CNOT gate to encoding the state I input and the accelerated state, then my code space, which is the state I really care about, is in this 2-dimensional state. And you also notice that this 2 state is invariant under these transformations. So this is a very analogy. I can take these transformations in analogy to my gauge transformation. So my gauge, the state preserves Gauss law would be this state in the code space, which are invariant under this group transformation, this symmetry transformation, right? So then they'll have this redundancy in the Hilbert space, right? We can the error correction code actually utilizes this redundancy to do the error correction. Basically, when you have some errors after this encoding, then you can measure whether the state after the error still stays into the code space. Right? If they are out of the code space, you see there are definitely errors happen during this evolution. This is a very analogy to quantum to the gauge theory encoding. Then we can ask the question, basically, what are the criteria that I want to keep the redundancy and do error correction, right? So this gives you another error threshold for these benefits. Basically, in the yellow region, the gauge redundancy plus quantum error correction gives me higher fidelity than the ones when I fix the gauge with Gauss law. So this is a very nice conclusion, and it really questions our previous encoding method. And the right way would be gauge redundancy plus quantum error correction. And this is all I want to say about digitization. Then let me talk about the propagation part. So basically, for a given state, I want to evolve the system based on the Hamiltonian. You can come to the analog one, which means your Hamiltonian matches the analog system pretty well. And then there's also this universal quantum computing, which actually I was indicating for the previous talks, for the contents in my previous previous slides. The universal one means you can build up the time evolution operator out of the building blocks of 1 qubit and 2 qubit gate with some errors that is smaller than epsilon. This is the time evolution operator that we really want to simulate. And this is the one that can really efficiently build out of 1 qubit and 2 qubit gate. Right, so there are also a lot of methods to do this approximation, like the trotterization or Taylor expansion or quantum singular value transformation. These methods are all mathematically very nice. And if we want to consider their convergences when we decrease the epsilon, and also consider their implementations on a quantum computer, they have their own pros and cons. It's still under investigation. Let me give you a very nice, this is some other methods. I will not talk in detail, focus on the trotterization. These 2 plots are very nice hints of our the possibility of the future. So the left one shows you as a function of year how the gate counts for specific problem could improve our algorithms. You will see the gate count cost decreases exponentially every year. Will really improve the algorithm by a lot. And this right plot shows you in what year we are able to do the heavy ion collision simulation. So this is under the assumption that the qubit number increases by a factor 2 every year, and also the algorithm improves exponentially every year. So basically, in 2043, we are able to do heavy ion collision. So it is a very nice projection for this field, and it provides some promise. And also for the propagation, for the trotterization, basically, as I said, we have the Cooke-Saskine Hamiltonian, which has the kinetic term and the potential term. If we want to implement this term, when we put down the quantum computing, we are going to use the totalization. Basically, you simulate every term for a small delta step, for a small time, which is delta t, and then you repeat this procedure for t divided by delta t times. Right, then the error will be proportional to delta t. So if you to take delta t to be very small, then the approximation to the exact one would be very good. To give you one example of the propagation, this is Z2 gauge theory. We consider Z2 gauge theory, and then you can build up its time evolution under this rectangular loop. If I only consider the rectangular part in the potential, the quantum circuit to do the time evolution is this one. You have a bunch of CNOT gate. And this is a very simple theory in comparison to the gauge series in the standard model. And you will consider this time evolution on a quantum computer, and then you will see that the quantum noise actually dominates the output. For example, if I consider the real device on IBM, under certain the whole thing, the whole time evolution gives you the identity matrix. However, after these operations, because of errors, I'm not going to recover the input state. So that quantifies the errors. So the fidelity, if I calculate the overlap for between the final state and the initial state and take score, the fidelity would be only 0.55. This is a pretty low fidelity. This is only for the rectangular part in the potential. If you consider the whole Hamiltonian evolution, the fidelity drops to 0.25. So basically, we have a quantum error dominate output instead of the ability to extract some physical observables. So this is the status, and but as I showed you the roadmaps, the quantum device is really improving a lot, processing very fast. So we have hope to improve the calculations and then extract physical quantities out of it. And then it's reaching the observables. As I give you the algorithm, we still need to prepare the state. Here is a small demonstration of preparing a SU2 proton out of gluons and quarks. Basically only quarks, because the gluon in 1+1 dimension can be integrated out. Then there's this variational quantum eigensolver potato, the algorithm, quantum algorithm that helps us to prepare the proton state. And this is one example of the initial state preparation. And then you also need to consider the measurement. For example, the PDF is a time-separated correlator that we want to measure. However, for each time slash, when we do the measurement, it collapses. So it's very hard to extract the time-separated correlators. And this is one example that we can do this measurement based on the toy models. Basically, you can do a time, instead of measuring the operator, you can put the operator into the unitary time evolution and then take some derivatives with respect to it. Also, we want to consider the systematic uncertainties. There you have finite volume effect and the truncation errors and convergence, which could destroy the resonances in the continuous series. This is a demonstration. When you increase from the left to right, when we increase the size of the volume and the truncation errors, you can see the resonance, which is really there in the continuous series. But if we use a smaller volume, I'm not able to see this resonance. And then also, as I mentioned, there's also error correction and mitigations involved in every steps. I will not go into detail about this, as we already see the fidelity is pretty low at this moment. But we can implement some error corrections, these polytwinings. The fidelity is still not very good at this moment. And then we have the continuous limit extrapolation problem. After we have done the previous procedures. Basically, we want to take the discrete space and digitize the discrete time into continuum. So you want to first extrapolate to the continuous time limit and then extrapolate to the continuum space limit. That would be the physical observable that we are interested in for the continuous space-time theory. And this is proposing a specific trajectory when you take the continuous space-time limit, which could save a lot of resources, where I will not go into details. And then there's this benchmark studies beyond the whole framework. You can also study some toy models to demonstrate the advantage of quantum computing. For example, the parton shower one, which is studied in these papers, and they give this very nice toy model. Basically, you put two flavor fermions and the scalars in the theory, and then there will be splittings. When you have one phi, the scalar field will split to fermions, and then the fermion would also split out fermions plus scalars. When you consider this, Lagrangian have different splitting trajectories. Basically, for our classical method, we can only calculate the probability of this splitting trajectory and plus the probability of this splitting trajectory. But for quantum computing, we're able to sum the amplitude of these two processes and take the square. That would help us to take into account the interference between these two trajectories. That is like a very nice aspect of quantum computing. You can include the quantum interference in a calculation. And another example is the bubble collision, where you can consider this toy model is a 1+1 model, and build up the configuration where you have two bubbles and move into each other. And then you can study what are the particles produced out of this collision and instruct certain observables. The results in this paper are also still based on that classical method, but which does not provide you good convergence to include to evolve the time to a very sufficiently long time, right? You will see there are some it's not converging for this observable as you take the time for the on the x-axis to a very large number. So this one demonstrated the limitation of the classical method for highly entangled state simulations. That's actually motivated the quantum simulation. And then I want to mention this benchmark, which is specifically for prestigious for our guest Tuosi. This is a lattice holography on quantum computer, where you can study this hyperbolic lattice, and there is this ADS-CFT correspondence between the bulk and the boundaries. Basically, we consider the correlation function between these 2 points on the boundary, which is the gray banded region. So then the correlation function, it could be related to the distance when you traverse into the bulk. It could also related to the distance when you traverse, when you just traveling along the boundary. Right, for the bulk theory, if it is a gaps theory, you will see the correlation function has an exponential decreasing. It's the exponential factor has a mass dependence. The mass is the mass of the bulk theory. But if you consider that this hyperbolic geometry as a distance traversing the bulk is logarithmically depending on the distance on the boundary. So in that relation, we'll calculate the boundary correlation function. You will observe a power law dependence of a distance. What is shown here, the correlation function on the boundary is a function theory because you don't have intrinsic skew on the boundary. The correlation function is a power law function. Actually, for this state preparation, if you have a very large system for the hyperbolic lattice, it's very hard to prepare this skew invariant state. And in this paper, we have demonstrated it's possible to use quantum computer to prepare this state with a diabatic evolution. And what is shown here, you can observe this very nice power law dependence of the correlation function as a function of the boundary distance. Right, this method could also be extended to larger lattice. Here, the largest volume we consider is 85 qubits, but you can consider the next, you have 4 layers or 5 layers, even very larger lattice volume. And then this is what I have today. I want to conclude. Basically, it's the very time that we want to consider quantum simulation for QFT and also some interesting benchmark studies in handed physics. There are a lot of things to do, like theory investigation, algorithmic development and benchmark study, and also hardware co-design. So I will stop here and look forward to questions. Any questions?
Thank you. Also, can I ask a question?
Sure. Yeah.
Can you go back? Sorry. Here.
Yeah.
I think if R if R is increasing like 1.5 or in red line, it don't show power behavior, right?
Yeah, exactly. So because when you count the distance, this is a periodic function. And
Yeah.
the deepest, the longest distance is this minimum value, this 1.5 or so. It's 10 to the 1.5. And then we'll traverse on the boundary the rest in this direction. The distance in this direction would be actually the distance will go the other direction. So this is the symmetry between the distances.
I see.
Yeah.
Okay, thanks.
Thanks for the question. Yeah, you can actually do more when you prepare the state, like measure the entanglement entropy and the thermodynamics and test whether there's phase transition on the boundary, etc. But this is only a demonstration that quantum computing is able to prepare the skew invariant state for a very large volume.
Can I ask one more question? Can you go back to gauge invariance, gauge redundancy, and quantum error question? I still don't understand that part. Can you go next slide? Yeah, I don't understand this figure. Sorry.
Right. So for this figure, we consider what is the parameter space that gives us higher fidelity when we consider the gauge redundancy, digitization method plus error correction. So if we consider like there are two digitization methods. One is I keep the gauge redundancy and I do quantum error correction. The other one is I can remove the gauge redundancy, only consider the Hilbert space that is invariant under the gauge transformation, which is basically satisfy this relation. It satisfies the Gauss law, the state. And then when we can ask a question like in what parameter space these two encoding method, digitization method gives us higher fidelity. Right, basically it's more resilient to quantum errors. For the yellow region, we would prefer the gauge redundancy from quantum error corrections. Right.
I see.
This puts some requirement on the hardware. So if the error threshold is error rate is below these red lines, you would rather consider gauge redundancy and do error corrections, even though it costs a larger number of qubits.
I see. The utilization of gauge redundancy to quantum error is new idea in this paper.
So the people have considered the Gauss law as quantum error corrections. But here we really answer the question in what condition we should consider this method.
Okay, thanks.
Any other question?
Can I ask one more question? What is a bottleneck for application of real physics? Where is the bottleneck?
Right, I would say it's the quantum errors, because nowadays if I want to increase the quantum circuits, I also need to consider the errors, quantum errors, how much, like the length, the depth of circuit depth, the depth of the circuit is limited by quantum errors.
Oh.
Also, the number of qubits for different devices, they have different limitations. Like for trapped ion, it's a little bit challenging to extend to a larger system to increase the number of qubits. But for the superconducting processor, the limitation is from quantum error correction from if I want to increase the number of qubits and the circuit depth.
Increase the number of qubits and quantum error is kind of independent, or is it correlated?
Yeah. For example, when you're like operating on different qubits, you could lose some coherence, right? The state loses some coherence.
Oh.
Yeah. That will be a hardware problem that I didn't consider much. I will consider it's possible to use it for quantum calculations.
Okay.
Okay, if there are no more questions, I think I can stop here. Then thanks a lot for this invitation, and sorry I cannot come because I have a visitor these days that's from coming a long way to visit me, so I cannot join you.
Thank you for your talk. And
Thank you, Sid.
is there other questions? Is there other questions? Yes. If no, we go to our second talk.
So yeah, thank you, and I will.
Oh, sorry. Talk to you later.
Yeah, talk to you later.
朱老师。
周老师我在。
如果你或者要不提前开始呗？
我可以的。
那你开始吧。
好。
你可以就是讲慢一点，然后可以提前结束，就是尽量讲慢一点或者。
好，我共享一下屏幕。现在能看到我屏幕吗？
可以。
我先退出一下，把那个摄像头打开。大家好，我是来自北京大学的博士后祝良贵。我今天报告的题目是引力波宇宙学的潜在偏差和爱见异巡天对推断引力波源形成环境的作用。今天报告的内容的话，主要是根据这两篇文章来讲的。这两篇文章是和陈翔老师一起合作完成的。那我将从以下4个部分来介绍今天的内容。首先，简单介绍一下研究背景。那当前我们宇宙学研究已经进入精确宇宙学时代，对各个宇宙学参数的测量已经达到很高的精度。我们也在此基础上建立了宇宙学的标准模型，就冷暗物质宇宙学常数冷暗物质模型lambda PDM。但是随着我们对各个参数的测量精度的提升，也引发了新的宇宙学危机。这个危机就是对同一个宇宙学参数用不同的方法测量的结果不一致。其中最显著的就是对哈勃常数的测量。用液星、超新星和宇宙阶梯测量得到的哈勃常数值是偏大的，大概在73左右。 用宇宙微波背景辐射 CMB 测量推断得到的哈勃常数值偏小。那这个问题也被称为 hypertension。那为了解释，就这个 tension 已经对宇宙学标准模型 lambda CDM 提出了挑战。为了解释这个问题，研究者的话就提出了很多候选的解释方案。比如我们可以在晚期宇宙或者早期宇宙修改或者增加一些物理过程，比如说修改引力或者是添加早期的暗能量等等，让宇宙膨胀在晚期的时候会自然的加快，使之符合夜星超新星的观测。当然，我们也可以，当然也要检查宇宙距离阶梯是否准确，因为宇宙距离阶梯是一个系统性的一个工程吧，应该说它从近到远要逐级校准，它可能存在潜在的系统偏差，所以也有一部分科学家在重新检查宇宙距离阶梯是否准确啊，检查我们对临近晚期宇宙的膨胀速度测量是否准确。当然，一种可能更客观的一种新的方法是，我们寻找新的能够测量宇宙膨胀的工具。很早之前的话就提出了强引力透镜，它的测量结果现在是偏向夜星超新星的测量结果了，但是它对模型的依赖性比较强，修改之后可能也就是现在还没有定论。那一种新的能够测量宇宙膨胀的方法的话，是我们现在是需要的。其实引力波就为我们提供了这么一种工具。那根据广义相对论的话，我们能够从理论上推导出引力波的相位信息是由引力波源的质量成分决定的。有了相位信息，我们能够直接推断出引力波源的质量。再有了质量，我们能够计算引力波传到观测者的时候它应有的振幅了，然后就能够因为它的振幅是反比于光度距离，就能够直接推断引力波源的光度距离信息，而不需要宇宙距离阶梯的校准。因为引力波可以让我们直接测量光度距离信息，所以因此称为标准气体，可以用于推断宇宙膨胀。那推断宇宙膨胀有了距离之外，我们还需要红移信息。但是不幸的是，引力波源的质量和红移是简并在一起的。我们通过引力波观测一般是不能直接推断引力波源的红移，我们通过其他的手段来推断引力波源的红移。推断引力波源的红移的方法的话，现在可以归类为6种，细分的话可以分为9种。第一种是看它引力波源的电磁对应体，有了电磁对应体，我们就可以找到它的宿主信息，然后通过光谱准确的获取引力波源的红移。那如果不幸的话，没有电磁对应体，比如说双黑洞闭合或者很远的引力波源，它的电磁辐射很弱，看不到的时候，这时候我们可以通过星系的星表来间接的指示引力波源的红移。因为引力波源，我们现在关注引力波源都是致密双星产生的，它是恒星演化的产物。那恒星的话，处在星系当中，星系更密集的或者更大的星系里面，产生引力波源的可能性更高。那这些概率就间接的指示了引力波源它的红移分布。那当然了，如果我们能够知道引力波源的质量的话，就它本身的质量，我们就能够，因为我们测量的是引力波源红移后的质量，我们能够知道引力波源本身的固有质量的话，我们就能够将红移后的质量直接除以它的固有质量，得到红移的信息。那这个的话，针对不同的引力波源有不同的情况，比如说对于双中子星并合，它的双中子并合潮汐形变的话，它会影响引力波源的相位。这个潮汐形变是和引力波源的固有质量决定的，或者是中子星它有个质量的上限，这个质量上限如果能看到很高红移的双中子星并合，它本身我们测量的红移后的质量偏大，除以它的上限，也能大概推断出中子星它的本身处的红移。那最后的，如果黑洞的话，它如果能知道黑洞的它的质量分布，我们也能反对黑洞的它本身的红移，因为黑洞恒星演化产生它会有一个概率分布，在某些质量范围，它会显得更可能一些。 其次的话是我们可以，第四种是我们如果能知道引力波源并合在某些红移的可能性更高，我们也能根据这个统计性的推断出引力波源红移。当然，第五种就是强引力透镜效应，这个在电磁方向也是，电磁观测里面也是适用的。最后一种是宇宙加速膨胀对引力波相位的一种修改，我们也能够直接的推断引力波源的红移，直接推断宇宙膨胀的一些信息。当然，这两个可以简单分为两类，前两类是要引力波和电磁观测结合的，然后剩下四种是只要引力波观测就可以，但是它们也有各自的优缺点。比如说要看电磁对应体的话，我们需要计时的后随观测才能要找它的电磁对应体，要协调各种望远镜同时就马上进行观测等等。那如果用巡天信息星表的话，它需要有比较完备的信息星表。如果是通过引力波源和星系做互相关的话，它需要很大的样本等等。那如果只用引力波来推断引力波源的红移的话，它也有各种依赖，比如中子星相关的话，就依赖于中子星的渥太方程；黑洞的话，依赖于黑洞本身的族群模型。那根据并合律来推断引力波源红移的话，就依赖于具体的恒星演化成黑洞的这个具体的模型。那根据强引力透镜的话，我们依赖于透镜模型，也依赖于宇宙距离对偶关系。那剩下的最后一种，如果根据信号直接推断宇宙加速膨胀的话，它其实是依赖于信号的强度，而且要需要很长的观测才能做得到的。总的而言的话，其实最方便的就是利用信息星表来间接的结合引力波源的光度距离信息、天空定位信息，间接的来指示引力波源的红移。因为在这种情况下，我们引力波探测推断的引力波源的天空位置和光度距离信息之后，只要从巡天信息星表里面把它的候选数组信息筛选出来，就可以直接对宇宙学膨胀的信息进行一个估计，就不需要其他的什么操作。它基本两个过程，信息巡天它是可以单独的做，引力波探测可以单独的做，最后分析的时候将两者数据结合起来，这个是比较方便的一个方法，也是最朴实的一个方法。那我们利用引力波探测和电磁观测的数据推断宇宙膨胀的话，它整个逻辑可以用这个图表示。首先，引力波探测得到的引力波源的天空定位信息包括光度距离和天空位置，然后告诉我们，然后我们去找它的电磁对应体，找不到的话就找它的候选数组星系，最后得到一个它的红移信息，最后通过拟合光度距离和红移的函数关系，推断得到对各个宇宙学参数的后验概率分布。这个后验概率分布就表明了我们对这些宇宙学参数的测量结果。整个分析过程是用贝叶斯分析框架来完成的。这欧米伽矢量是代表各个宇宙学我们关注的各个宇宙学参数 ，xGW 是我们的引力波探测数据 ，xEM 是电磁对应体的观测数据。宇宙学的后验概率可以表示成矢量函数和鲜艳的成绩，它乘以一个 evidence，就是它的一个规划项。如果只关注对参数测量的误差的话，其实分母规划项是可以忽略不计，直接关注它的矢量函数和鲜艳的成绩。它的矢量函数的话可以进一步展开，矢量函数最后可以展开成3项，一项是对 Pi 是 xGW 引力波数据的观测数据，它提供的信息是对光度距离、天空位置的一个概率分布，然后是 xEM 的一个矢量函数，最后是关于红移天空位置一个先验。如果针对是暗气敌的话，其实我们是没有看到它的任何电磁信号的 xEM 是个空集，这里就是一个常数。第二项， 如果是有电磁对应体的话，这个电磁对应体提供的就是引力波源的红移，当然也包括其他引力波源的参数，比如说引力波源双星它的双星轨道面的指向和我们视线方向的倾角。第三项它的鲜艳的话，是表明引力波源它可能所处的红移和天空位置。这个鲜艳是，如果我们用星系星表来指示引力波源的红移信息的话，这个鲜艳其实代表的就是我们巡天星系星表。它具体展开的话，其实就是我们巡天星系星表的一个累计，就包括它的星系的红移、天空位置、阿尔法、德塔的经纬度等等。那通过这一套计算，其实就是在拟合光度距离红移关系。那 LIGO 的话，它目前已经运行了三轮引力波探测，已经公布的90例引力波事件，其中包括第一例双中子星并合 GW170817，它是实现了引力波和电磁波多性时观测的一例事件，它得到了一个很精确的红移。那剩下的它包括80例左右的双黑洞事件，但是它要用于宇宙学推断的话，它需要有比较准确的天空定位精度，所以它只有LIGO目前官方公布的结果只有46例用于了宇宙学，就宇宙膨胀的推断。那结合双中子星和46例双黑洞并合事件推断，对哈勃常数推断结果就如右下角这个图所示，它的精度大概在10%左右。10%的话，离澄清哈勃 tension 这个问题的精度远远不够的。那接下来因为 LIGO 它的引力波探测取得了很大的成功，就激励了很多新的引力波探测项目，比如空间的话，也有空间很多探测项目，比如说欧洲的 LIFA，我们中国自己的天琴和太极项目等等都好。那接下来因为 LIGO 目前的探测器 Advanced LIGO 称为第2代地面引力波探测器，接着下一代的话，其实推出了更灵敏的引力波探测器，比如说欧洲的爱因斯坦望远镜 ET 和美国的宇宙探测者 DE。那它就空间和地面，它的引力波探测计划针对的就探测对象不太一样。有空间能用于宇宙学推断宇宙膨胀的引力波源的话，包括恒星级质量黑洞，它的能探测到数量级大概在0到100以内，就1粒到100这个量级。对于极端质量比显微镜 M 率的话，它也是不确定度很大，就是大概1到1000的量级左右。对于大质量双黑洞并合，它的能探测到数量大概也是1到100左右的量级。为什么它的不确定度那么大？主要是我们空间还没有真实的去探测它，就没有真实数据，我们对引力波源的族群性质就了解的非常有限，所以不确定度也非常大。对第3代地面引力波探测器的话，因为 LIGO 目前已经运行了3轮了，对地面引力波探测器它的引力波源的族群性质已经有了很好的了解，所以下一代地面引力波探测器对引力波源的探测数量是比较好的估计的。对于暗气体，主要是双中子星、双黑洞并合等等的话，它大概有百万量级的数量。对亮气体可能能有1000左右的量级的能看到数量。那当然，根据这些将来能够探测到的引力波源对宇宙膨胀的推断结果的话，比如对于哈勃常数，对空间引力波探测器的话，它大概能做到几到0.几的精度。当然，这也是针对不同探测器和不同的引力波源，它有所区别。当然，空间引力波探测器它有个好处就是对恒星级质量黑洞，因为它旋进阶段的信号落在空间引力波探测器内，而它并合的信号落在地面引力波探测器内。如果能把空间和地面的数据结合起来分析的话，就能实现多波段探测。这时候它就有个能结合空间的对天空定位准的优势和地面信道比高的优势，结合起来能提供更准确的对 引力波源空间定位信息能更好的限制哈勃场。
derive the Friedman equations, and also we define the Eiffel number as the integral from the horizon crossing to the end of the inflation. So it also can be expressed by integral of the potential of the multi-field inflation. And also we use the delta n formalism to simplify our calculation. In this formalism, we set the initial time at the initial time t initial. We use the flat space-time gauge condition with zero curvature, and at a general time t, we select this gauge that the energy density is uniform, so we can write down the curvature participation in such a formalism, and also we could define the curvature perturbation in terms of e-folding numbers, and the n could be interpreted as the e-folding number in an unperturbed, uniformly expanding universe. And also, we write the curvature perturbation as the e-folding number of the inflation field. And under the first order approximation, we can express the curvature perturbation in terms of the e-folding number and the field perturbation, to significantly simplify the computational complexity. And also, we could calculate the two-point correlation function of the curvature perturbation in terms of the scalar field perturbations and the e-folding numbers in a uniform background, and also write down the power spectral density of curvature perturbations. And so is to the tensor power spectrum, and so we can acquire all the inflation parameters which could be linked to the observation of astronomy, the tensor to scalar ratio in terms of the formalism, and the scalar spectral index, the tensor spectral index, and the consistency relation. If we don't know much more information about the inflation theory, so this is the end of the story. But if we assume that the number of the field is large enough that we could and write down the specific potential, we can furthermore calculate all the results. And the Price have developed a fixed exponent multi-field inflation, and in which he write down the potential with this kind of thing, and the power of the field is fixed. And I developed the diverse exponent multi-field inflation with diverse power of the scalar field. So it is more natural and suitable for the and more general to the higher energy theories. So it's a phenomenologically theory. And also we use the horizon crossing approximation, in which the scalar field value at the end of the inflation could be neglected. So only the initial value matters. So we can write down the e-folding number as this simplified term. And so we can derive all the inflation parameters in terms of the specific form, the scalar spectral index, and other parameters. And in the manifold limit, or the large number limit, and we could assume the scalar field are in a probability distribution, that the the coefficients are in a probability distribution, and also the power is also in a probability distribution. So we can then calculate all the parameters and continue to calculate it. And we also provide a random distribution for such the value of the scalar field that the xi means the normal distribution. This corresponds to an average distribution on an nf-dimensional ellipsoid surface with the semi-major axis determined by the power. This is from the this equation. And as an example, we can simplify one of the power sum formulas into this thing. Summation, some emerge right here. And mathematically, for any normal random variable, the means of the powers, the means of the normal random variable powers is equal to this one. And f is a confluent hypergeometric function with the first can, and with the condition of mu larger than -1. And if the x is normal, is simplest normal random variable, then the f is equals 1, and the mean of the powers equal to this one, and the gamma is the gamma function. And there exists the quotient of the summation, so we should discuss it. For two normally distributed random variables alpha and beta, with the probability condition that the probability of the beta is larger than 0, 10 to 1, and so we can write down the quotient and with the mean and the standard deviation, and it is also approach a normal distribution, where the gamma mean is defined as the correlation factor. So according to the central limit theorem, in the multi-field limit, we can theoretically simplify all the summations and the results. For example, one of the summation term approach a normal distribution with such kind of mean, and similarly, other summations term to other kind of normal distributions. And this is an specific example. This kind of summation will be simplified to the 2 times n e-folding number and the mean value of the inverse of the power. This is a manifold central limit theorem, and if it is if the number of the field exists to the e to the 100 power, we can further simplify the integral and all the stochastic analysis through the Laplace approximation method. The basic idea of the Laplace method is that if the m is large enough, so only the term with the smaller p contributes to all the integral. So we can